So, good morning everybody. At least those of you who managed to arrive here despite of the snow so early in the morning. Welcome to Mixed Signal. Today I want to finish the switch capacitor topic and then we discuss the fundamentals of data converters. Let's review what we did the last two lectures. This was mainly the analysis and understanding of switch capacitor circuits. So I gave you this cookbook that gives you a basic understanding how to analyze switch capacitor circuits and which steps are involved. So the first thing was that we label a certain plate of all capacitors. This is something you can do arbitrarily. It's just labeling one plate, and the purpose is not to flip the cap around when going from one phase to the other. So to be sure during the analysis that you know which plate is connected to which node. So I made always this small plus sign there. You can also make a dot or something else. It's just a label and it has nothing to do with the polarity of the charge on the cap. Then the next step was to draw equivalent circuits in each phases. This is something that should help you to simplify the analysis, that you have one circuit without switches for the phase 1 and another circuit without switches for the phase 2. And then the third step is the most difficult one. This is this charge balance analysis, where you go back one period in time. You compute all charges on the caps at the respective time instance. Then you calculate the charge transfer during the phase transition. So going from one phase to the next one, which charge is transferred. You have to analyze the current path in order to clarify how the charge is shifted in the circuit. And then you go from one period in the past till the present time instance, and then you get a time domain equation of the output of your circuit. After that you make a C transformation of this equation, so you get a frequency domain representation of the circuit, and therewith you can compute a transfer function. The last step that is not always done is that you evaluate this transfer function on the unit cycle, and here you can compare it with the continuous time transfer function of the circuit that you want to replace by your switch cap circuit. So these steps, I showed this for two examples. I guess you will show it in the, you will exercise in the tutorial. Thanks, Michael. So my question for you guys is this clear how to do it in principle? Or is there a fundamental question that you say, okay, I did not understand this point? Okay. So I already said it. I strongly encourage you to exercise this 1 or 2 times on your own to really understand how this works. Okay. Then last lecture we stopped with this switch capacitor amplifier. We have seen that in one phase we discharge this cap because we connected between the virtual ground of the op amp and here the ground on this side, and during that time the op amp is reset, so we close this feedback, apply a ground to the other input. So this feedback assures that the operational amplifier works in linear mode of operation, and only then, if it works in linear mode of operation, we have this virtual ground at this node. Then in the phase phi 1 we connect the input to this cap. Still here is the virtual ground, and hence we have a charging current for the first cap flowing here from the input into the cap, charging up this cap to the input voltage, and the current flows like this. It cannot enter the op amp, so it has to go through the second cap in the feedback branch. So all the charge that is flowing on the first cap is transferred to the second cap. This charge causes a voltage drop across this second cap, and this voltage drop is equivalent to the output voltage. So this was the last thing we analyzed last week, and I ended with this picture where we said, okay, we have always two phases. We have an amplification phase phi 1, where the output is the amplified input signal, and in the phase phi 2 the op amp is reset, which means that it is either 0 volts at the output, or for the case that we have a finite offset voltage, the op amp is reset to the offset voltage. And then we saw, for more realistic consideration, we cannot have these steep steps here, but in reality with an op amp with a finite slew rate we always have a settling when we change these phases. So in reality the input signal looks more like the red one. And my last question last week was, what is the impact of the switching between the amplified signal and the reset state? So what do you think? What is the difficulty designing a circuit like this? Well, if you look at the red curve, then you can already see the problem. By switching between these two states, and because of the requirement that the voltage changes so much in each phase, from a finite value to 0, then back to a finite value, then back to 0. So there is lots of charging and discharging of caps in this circuit. So usually such a circuit is slew rate limited by the op amp, or we can also say the speed of the circuit determines here the required slew rate. So the operational amplifier design is quite tough here. So then if you look at this circuit, you might say it is not required that we go back to 0 all the time. Perhaps it's sufficient if we hold one value, and then we have to charge only the difference of these two states. Then here we keep the value again, keep it constant, and then we follow here and keep it constant at this point again, and so on and so on. So by doing this, there is the average height of voltage that has to be switched is reduced. So the question is, how can we modify this circuit in such a way that we keep the output voltage constant during the second phase, during the previous reset phase? And this can be done by a circuit that looks like this. Here you have a circuit that has even more switches, and that looks on the first glance very complicated. So let's start with our Cookbook approach and draw equivalent circuits of this basic circuit. So the first step is that we label the polarity of the cap. So I might define here, I label this plate, and I can label this plate and this plate. So by doing this, I don't think about the actual polarity, I simply choose one plate. But after labeling them, I'm not allowed to change it during the computation. So now, from now on, I have to keep this labeling. So in a phase phi 1, the circuit looks like this. I have this switch connecting this cap C1 to the op amp. So I have here the C1, with this labeling connected to the op amp. Then I have this switch. This one is off, but I have a cap C3 connected to ground here and on the other side to the output of the op amp. So here I have a cap C3 with this labeling. And finally, the C2 is connected to the virtual ground and to the output of the op amp on the other side. So I have my C2 connected like this. Then in the second phase, I'll sketch it here, phase phi 2. In the phase phi 2, I have this first cap connected to virtual ground on the op amp side and to ground on the other side. So this one is shorted. So I have the C1 here. Here's my op amp. So this I forgot here. Then the cap C2 is connected to virtual ground here and to ground on the other side. So I have a C2 connected like this. And the C3 is connected in the feedback of the op amp. So the C3 is connected like this. Okay, let's look at this. If we neglect the C3 for a moment, then we see that in the phase phi 2 both caps are discharged. Okay, similar to the previous circuit. Then in the phase phi 1 we have the configuration of this input C and a feedback C. So again, this C1 is charged to the input voltage. All the charge is transferred to C2 and charges up the second cap. So exactly the same as in the previous case. The only difference is that we now have a third cap connected to the output. So what is the impact of the cap? Well, in the phase phi 1 there is no impact. The gain is defined by the two caps C1 and C2. Circuit behaves exactly in the same way as before. However, the output voltage now is stored on this cap C3. So we charge the cap C3 to the voltage that is defined by the other caps. And then when we go back to the second phase, then we take this C3 and put it into the feedback branch of the op amp. So we disconnect it here and put this point here to the virtual ground. And it is a virtual ground because we now have this cap in the feedback branch. So here is this C3. There is this C3 is still charged to the previous output voltage. No charge transfer occurs here. So we take the output voltage in the first phase, store it, and then we bring this cap in the feedback branch, and you can see that now the output here corresponds exactly to the voltage stored on this cap. So here we store the output voltage, bring it to the feedback branch, and this is our new output voltage. And that way we keep the voltage constant when going from phase phi 1 to the phase phi 2. And of course in the phase phi 2 the other caps are discharged to prepare for the next amplification phase. And for the next amplification phase, we take the C3 out of the feedback, connect it parallel to the output, and operation is again defined by C1 and C2. Okay, now you might say there is a fourth cap that I ignored so far. Well, this is a small cap that is always connected to the output and to this node. This is a cap that is not switched, and it's usually only a small cap that has the purpose to avoid glitches during the phase transition. So why is this? The reason is we said the operational amplifier can only work in linear mode of operation when there is if there is a feedback. Then we also said the switches for the two phases are never allowed to conduct at the same time. So we have a non-overlapping two-phase clock, which means that we open one set of switches before we close the next one. So in between there is a phase where no set of switches is conducting. And during this phase there is no feedback to the op-amp. If you have a very fast op-amp, this time can already be sufficient for the op-amp to flip to one side or to the other side and end up in saturation, or at least to cause a voltage spike. And in order to avoid this, in order to always have a certain amount of feedback, we have this cap C4, which can be ignored for our functional analysis of the circuit. Okay. One last thing I want to mention with the switch capacitor circuit is the property that we have now a time variant circuit, time discrete circuit, but it consists still of linear circuit elements. And in linear circuit theory, we have something like the superposition theorem. And the question is, can we apply this superposition theorem also to switch capacitor circuits? Let's go back to the switch capacitor integrator I already explained. Here we had an operational amplifier with, sorry, here I made a mistake, with an integrator C in the feedback. So let's call this CA. And then we can build the input stage like this and say, okay, here is the first switch, a cap C1, a second switch, and then we have two other switches here and here. And now let's assume that we control them like this. Here phi 1, here phi 1, and here we have a phi 2 and a phi 2. And if you go through your material, you find that our output voltage V out, this is the voltage here, the op-amp output, that this output voltage is given by C1 over CA times C to the power of minus 1, 1 minus C to the power of minus 1. You already know this. Now let's connect a second circuit. Let's take, for instance, an input stage like this, a second capacitor C2, the same switch configuration. Now we may change the clocks. We can now say this is phi 1, this is phi 1, the others is phi 2. Well, we can also do it in the other way. This is up to you. And now if we would remove the red circuit and connect the blue one to this node, then our output would be minus C3, no, minus C2, sorry, there's no C3, C2 over CA times 1 over 1 minus C to the power of minus 1. This is the blue circuit. The question is, what happens if I reconnect the red one and there is both the red and the blue circuit connected to the virtual ground of the op-amp? Well, what happens is that at this node we have a virtual ground. Okay? Independent whether one circuit or both of them are connected. Then we have a current flowing through the first cap, charging up the feedback cap. And we have a current flowing through the second cap, entering the same node, and then also flowing into the feedback cap. So what happens is that the red and the blue current are combined, summed up, and the sum of them enters here this feedback cap. So we can say we have a superposition of the two currents in the feedback branch, and the result is that our output voltage V out here is given by the transfer function of the red subcircuit plus the transfer function of the blue subcircuit. Therewith we have a programmable amplifier. No, sorry. Therewith we have an amplifier that can combine two inputs, one input voltage V1 and a second input voltage V2. So I said we can program this. There I was one step ahead, and therefore I want to copy this circuit again. Let's assume we have the same circuit. Here the op-amp with the feedback cap, and now assume we have one cap and let's say this is phi 1, phi 1, phi 2, phi 2, and the same thing again. Now I take really the same one. Here again phi 1, phi 1, phi 2, phi 2. I combine them here and connect it to the virtual ground. Now we can tie the inputs here together. Okay, then you might say this is the same as I would increase this or this cap by a factor of 2 because the circuit is in parallel now. So here I can now amplify the input voltage V in to generate the output voltage V out here. What can we do with a circuit like this? Any idea? So this is my last slide for switch capacitor circuits. then we start with data converters. So my question for you guys is, looking at this circuit, do you already have an idea how this can lead to data converters? So what is the gain we have here? So we have an output voltage V out, and this output voltage is given, let's give names to the cap. This is C and C, and this is CA. So we have C over CA times 1 over 1 minus C to the power of minus 1. This is one part. The second part is C over CA 1 over 1 minus C to the power of minus 1. Okay. Let's assume this is 1. And let's assume this is 1. Then the gain of the circuit is 2. If I disable this part and keep only one stage, then the gain of the circuit is 1. If I add a third one of these blue sub-circuits and connect it in the same way, and I enable this, then my gain is 3, and so on and so on. So here, by turning one of these stages on or off, I can alter the gain that my input voltage experiences. Okay? Let's say the input voltage is a fixed value. Then I can amplify a fixed value depending on the number of these stages I connected to the virtual ground. And what is this? Let's assume that I can control here the clocks of these switches in a digital way. I can either apply the clocks to the stage or I can keep the signals off in a digital way. So this is something like a digital to analog converter. If I have some means to turn one of these stages here on or off by turning the clocks of this stage on or off, I can alter the gain that the input experiences. I can do this digitally. The result is an analog output voltage. So this is a very basic type of digital to analog converter. Okay, this is just as a motivation. We will go through all this digital to analog converter circuits during the next hours. But this is a motivation that we can use this switch capacitor stuff already as data converters. So beside the fact that switch capacitor circuits are a good and robust implementation of analog functionality in the context of process variations, you should also see that this is a basic circuit technique that can be used in data converters. Okay. Questions so far? If not, we will start with the data converter fundamentals today. Before we look into the circuits of the digital to analog and analog to digital converters, I want to go through the performance figures and the characteristics of these data converters. This has two reasons. One is for those of you who will actually design data converters in the future, they have to know what is important in a data converter, what figures have to be defined, what figures have to be optimized. For those of you who won't design data converters themselves but want to use them For those of you, I want to give you an understanding of these performance figures, because this is the numbers that are given in the data sheets. So if you take a data sheet and see all these numbers of a data converter, then I want that you understand it in order to choose the most appropriate one for your application. So my question is, what is the most important performance figure of data converters? The most important one everybody should know and knows, I'm sure. So who wants to say it? What is the most important performance figure of a of a data converter? Let's say an ADC. What? The speed? Okay. Resolution is the most important one. So actually the number of bits. So, and then the fundamental question comes up, what is actually the number of bits? And we will see throughout this lecture that the number of bits is not exactly the number of wires coming out of this data converter. And hence it is worth to look into the details and to understand what other performance figures are there and what they actually mean in order to end up with a good definition of the resolution of a data converter. Let's start with the digital to analog converter, because this is the easier one. You can see here a block diagram of this digital to analog converter. We have a digital input word to this device. This digital input word defines then the output voltage that is generated. Then you can see that there is a third input to the D2A converter. And why is this? Well, the reason for this is that you need a scaling factor for the digital input word in order to generate the output voltage. So here you have just numbers, 1, 2, 3, 4, and so on. So the question is, what does these numbers mean? Does this mean we have 1, 2, 3, 4 volts at the output if we apply it to the input? Or does it mean that we have 1, 2, 3, 4 millivolts? Or something else? Or microvolts? Or what is the magnitude of this output voltage related to this input? And this is the purpose of the reference voltage. Our output voltage is defined, V out is equal to the digital input word B in times the reference voltage, V ref. And now we define the digital input word in the following way. We say the B in is equal to, this is a binary word here. So here we have something like B1, B2, B3, B4. And now we don't do it as I said before, to say we count up 1, 2, 3, 4. But now we define that the input word is B1 times 2 to the power of minus 1 plus B2, 2 to the power of minus 2 plus B3, 2 to the power of minus 3 plus B4, 2 to the power of minus 4, and so on and so on. So this means that we have the radix point here. The B in is a number that is smaller than 1. And why is this? Well, here it is only a definition, but it gives a reasonable understanding of the reference voltage. So the reference voltage is somehow the max value that you can achieve with your digital to analog converter. And you scale this reference voltage down accordingly to the input word given here by by this definition. So we can also find a short notation of this. This is the sum over bi 2 to the power of minus I for I equal to 1 to n. And now here n is the number of bits, which is not the resolution, but the number of bits coming out of the device. A graphical representation of the behavior of a DAC is shown here. Here on the x-axis you can see all possible input words be in. So for 2-bit device we have 0, 0, 0, 1, 1, 0, 1, 1. And each of these inputs results in a certain output voltage. And this output voltage is given on the y-axis. So here you can see a normalized representation. We give the output voltage in terms of the reference voltage, so normalized to the reference voltage. And for 2-bit device, you can see the smallest value is the 0, 0. Then we increment the digital input. So we go up here to 1 over 4. We increment here again. We go up again by 1 over 4, end up by 1 over 2. And here we can continue like this. So we say if we go, or if we increment our digital input by 1 step, we say we increment this by 1 LSB, where LSB is the least significant bit. And if we increment the digital input by 1 LSB, the output should be incremented by 1 voltage step, and we call this 1 VLSB. So the voltage increment corresponding to 1 LSB, corresponding to 1 step. So going 1 step up in the input increases the output by 1 VLSB. So we can say that VLSB is given by the reference voltage Vref divided by 2 to the power of n. And by doing this we can say 1 LSB is equal to 1 over 2 to the power of n. The interesting thing is that the values we get here is defined only at discrete positions. So this is only points. There is nothing here in between. And the reason for this is that in between two subsequent values of the input word, there is nothing in between. Okay, if we have only 2 input bits, then we can go from 0, 1 to 1, 0. But we don't have a position in between, and obviously hence there is no output here. There is a discrete set of inputs resulting in a discrete set of output voltages. The other thing is, you can see this one is missing. So here you can see we don't reach the reference voltage exactly, which is clear because this would require a 3rd bit. And you can see it also here, according to this definition, even if you set all bits to 1, you don't reach the 1 exactly. Okay? This one corresponds to 1 over 2. This one corresponds to 1 over 4. So we have already, this is 0.5, this is together with this one is 0.75, and so on and so on. You can add more and more bits, but you will never reach the 1 exactly. And hence this point here is missing. So you can see the reference voltage also as an upper bound of output voltages that you can reach here. So we have a max output voltage, and this maximum output voltage V out max is given by Vref minus VLSB. We are always 1 VLSB below the max value. So that's it. That is an ideal characteristic of a of a digital to analog converter. If everything would be like this, then it would be perfect. Then there would be no problems during the design of data converters. Unfortunately, there is lots of impairments that can affect the shape of this curve. And I want to start to go through potential problems that may occur and to analyze the impact on this converter characteristics. The easiest failure that can occur is the so-called offset error. The offset error is a shift of the complete characteristics into the voltage direction. So you can see on the previous slide the first point where the I shouldn't shift it. The first point where all input bits are set to 0 results in a 0 output voltage. If we have another output voltage here, for instance like this, then you can see for all 0 input we have a finite output voltage. So you can see that the complete characteristics is shifted up. The voltage by which this characteristics is shifted up is called the offset of the DAC. So we have an offset error here that is defined by the voltage shift. And you measure this for the very first point that should be normally 0. Then you can of course give this number in terms of volts or millivolts or whatever. However, if you give it in absolute numbers, then it is hard to say whether this is a large or a small error. Imagine that you have a device that generates voltages from 0 to 10 volts. And you say, okay, my offset voltage is 100 millivolts. Then this is a smaller offset error than if you have a device that generates voltages only in between 0 and 1 volt, and you have the same 100 millivolts offset. So the question, is this a large or a small offset error, depends on the voltage increment that you can achieve. So it depends on the VLSB, and hence normally this offset error is not given in volts, but it is given as the output voltage normalized to VLSB. So to determine the offset error, we measure this voltage here. This is the V out for all input bits set to 0. So this means all inputs set to 0. And we measure this voltage and normalize it by VLSB. And this is what we call the offset error of the DAC. The offset error can be seen as something like this. Here we have the DAC. We have our reference voltage, Vref. We have here our input bits, B in. And this results in a voltage. And now we add the offset voltage to this in order to get the output voltage. And at this point we add the offset. So this is a model for the offset error, something that is added to the output. The second error that can occur in DACs is a little bit more complicated, but still one of the good errors. I'll come to that one later. This is the so-called gain error. So what we have seen so far is that we can shift a curve up or down, and this is the offset voltage. What we can also do is to alter the slope of this curve. And curve means the line connecting all these dots. So we can alter the slope, and this is what we call a gain error. So let's assume that we have an ideal case here. The red dots are the ideal ones, and now we have altered the gain. Then the question is, how can we characterize this? So this one is characterized by saying, okay, we take the output voltage for all bits set to 1. This is this voltage. This is V out for all bits set to 1. And we take the output voltage. Sorry, this is not really straight lines, but I hope you understand what I mean. This is the output voltage V out for all bits set to 0. And then you measure this distance and normalize it to VLSB. So this is what we have here. We take the output voltage for all bits equal to 1, normalize it to VLSB, and we subtract the output voltage for all bits set to 0. So this one is actually the offset. And if we look at the red points, then we see for an ideal A to D converter, this is 2 to the power of n minus 1. So this is for an ideal converter. So the offset error is defined by measuring this voltage here and comparing it to the value that an ideal converter has. And an ideal converter has here a difference of 2 to the power of n minus 1. And this is a characteristics for the change of the slope of this converter. This is the so-called DAC gain error, and this is again something that can be modeled easily. We have here a DAC with reference voltage, the input bits, and here we can add a gain element that describes the gain error. If we look at these two block diagrams, then we can see that this is both the gain error and the offset error is something linear. We have a scaling element, or we have an adder that adds an error to this. This is nothing non-linear. And next week probably we come back to non-linear errors in DACs. And always non-linear errors give rise to harmonic distortion and are much more difficult to compensate in the system. A gain error can be relatively easy characterized in your system and then compensated. Offset error is usually even less critical because circuits often work on differences and cancel out constant components. However, it has to be considered. For instance, if you think about a closed loop circuit that contains a DAC, if the gain of the DAC changes, then the loop gain changes and your loop dynamic changes. Hence, it is important to understand that something can occur and to understand what it is and also where it might have an impact. Okay. Let's do the same thing for analog to digital converters. The analog to digital converters can be again described as a device that now has an analog input voltage and generates here a digital output word. So here we have one wire carrying a voltage and we get out several wires carrying the information of the input voltage. And again we can say we have here the reference voltage Vref times the digital word, which is now the output, so we call it B out, and this is equal to V in. And again we can define this as Vref times the sum over all the wires coming out, I equal to 1 to n over bi 2 to the power of minus I, and this is equal to V in. Is this correct? So probably if I ask like this, answer is no. But why? Let's look at the curve on the right hand side. On the x-axis we have all possible input voltages, and on the y-axis we have the output words that can occur at the output of the device. You can see here we have a continuum of values. You can take a voltage, you can take another voltage, and independent on how you choose these voltages, you can find a voltage in between. Take the new ones, and you can again find a voltage in between, and so on and so on. There is a continuum of input values. However, there is a discrete set of output values. So obviously, this equation here, where we say a discrete, bring it back. Here we have a discrete set of values, and here we have something continuous. This cannot fit together. So this equation is only valid at discrete points, so it is valid here, it is valid here, here, and here. At these points you can fulfill this equation. At all other points you cannot fulfill it. You can also see now we have, as the input is continuous, we have in between these points we have really other values. And for all these other values, this equation is not fulfilled. So we have to add here a correction term, Vx, which is the so-called quantization error. And we have to add it here too, Vx. And we can state that the Vx is given by minus, let me remove this again. We can say the Vx is always larger than minus 1 over 2 V LSB but smaller than plus 1 over 2 V LSB. And this is valid as long as we stay in the range of operation and the range of operation is given by minus 1 over 2 to the power of n minus 1. I explain this immediately. N plus 1. Smaller or equal V in over V ref. Less or equal 1 minus 1 over 2 to the power of n plus 1. Otherwise we have a saturation, or we can say an overloading. So these borders mean that we have to stay in these bounds. Otherwise, if we increase the voltage further, this cannot change anymore because we already have set all bits to 1. The voltage increases even more, so the quantization error goes up and up and up. In this representation you can see that the quantization error is the voltage, or is the difference in terms of voltage between this dashed line and the blue step function, the quantizer function. Let's look at this quantization error more in detail. This is a circuit that can be used to extract the quantization error. Of course, nobody builds a circuit like this, but it is good for understanding what the quantization error is and how we can compute it. Let's take an input voltage ramp here and apply it to an ADC. The ADC translates the input voltage into a binary word, but it adds some quantization error. So here we have a representation, a digital representation of the input plus a quantization error, and then we bring this back with a DAC. So we have a voltage again that contains now the input plus the quantization error. If we take the input voltage again and subtract it from this V1, then we have here only the input. Here we have the input plus the quantization error. So if we subtract this, we get only the quantization error. And then you know all these pictures where we say, okay, we go up with a signal. Here we have the input ramp like this. Then the output of the DAC makes something like this. And if we subtract this from each other, then we get this quantization error. So the quantization error is a sawtooth-like signal like this. So as it repeats all the time, we can say, okay, let's limit our investigation now to one period where we say, okay, here we have 1 over 2 t, and here we have minus 1. Okay, there's no room. Here we have minus 1 over 2 t. Then the max value is 1 over 2 VLSB, and the min value is minus 1 over 2 VLSB. So my question now is, how can we characterize this quantization error? And if we have a signal like this, then it's usually good to compute the power contained in this signal and to compute the average value. So if we consider only one tooth of this sawtooth signal, then we can say we have a VQ Q is the quantization error, and this is equal to minus V LSB over T times T. This is only a description of this curve. Okay? V LSB over T times T. And we can say the T is in this interval minus T over 2 and plus T over 2. So to compute the average value, we can say the VQ average can be calculated by averaging over this signal. So we have the integral from minus T over 2 to plus T over 2 over the VQ dt. And you can see if you insert this that this results in a 0 mean value. So we have a mean free quantization noise here. Well, this applies to the case where we have a ramp at the input, and this ramp at the input results in this sawtooth-like quantization error. And you can see here is positive values, here is negative values, so in average this is mean free. Of course you can say it is an unrealistic case that we apply a ramp to a data converter because we already know what comes out. But the point that it is mean free is also true if we have an equally distributed random input signal. So if we are equally distributed anywhere, this can be also computed, we will do it during this lecture also at some point, then again the quantization error is mean free. However, it is not a zero signal. Also it is mean free, there has to be some power contained in this signal. And hence we want to compute the quantization noise power contained in this signal. And this can be done by saying, okay, we have a quantization noise power, VQ square average. We can compute it in the same way. Now I make it in a little bit more detail, because this is important. We have 1 over T. Then we have the integral from minus T over 2 to plus T over 2 over VQ square depending on T dt. So I can insert this, then I have 1 over T, the integral over V LSB square over T square times T square dt. And this yields V LSB square T to the power of 3. This is this 4 factor. Then we have to integrate the T square. This is 1 over 3. T to the power of 3. And then we have to insert these boundaries. So this yields T to the power of 3 over 8 plus T to the power of 3 over 8. And at the end we have, I put it here, we have V LSB square over 12. And this is a very important formula because it gives, this is very often used in the context of data converters, that the quantization noise power is given by VLSB square over 12. Or we can also express it by the reference voltage. We can say this is Vref square over 12 times 2 to the power of 2n. This is simply inserted the definition of the VLSB. Okay. And you can of course also compute RMS value and can say VQ RMS, this root means square, so it's simply the square root of this. So we have square root of VQ square average, and this is VLSB over square root of 12. This is the power of the quantization noise. Oh no, the power of the quantization error. And I said several times quantization noise. Why is this? So if you assume not a ramp, but a random signal, then this quantization error is distributed randomly. Well, of course, it is still deterministically dependent on the input signal. Each input signal corresponds to one exact value of the quantization noise. But if the number of quantization steps is large, then in terms of these pictures you have lots of these tooths, and they are always in between plus minus V LSB over 2. Then this quantization error appears as random signal, as a noise signal. Also it is not, but it appears as a random signal and is during most considerations and calculations of data converters in good approximation assumed as a noise signal. And hence people often say it is a quantization noise. Also it is somehow pseudo noise. Okay. Now we know the power of this quantization noise. And again the question, it is lots of noise or less or little noise, depends on the question how big is the signal. So what we always have to do is to compare the noise to the signal. And this is the so-called signal to noise ratio. Let's assume a sinusoidal input signal. So let's assume a sine signal with an amplitude equal to I take the max value, V equal to 1 over 2 V ref. Why 1 over 2 V ref? Well, this is the max value that I can produce with my DAC. Okay? So if I have here the values V out that I can generate, here's the 0. Here's my max value, so this is V ref minus V LSB. So then we have here approximately V ref. Okay? And if I want to put a sign in this with the max amplitude, then such a sign can have only, okay, sign, okay. Then the amplitude here can be only 1 over 2 V ref. Okay, that's why I chose this value. This is the maximum sign that I can process with this converter. Good. However, then the power the signal power is then given by, you know this, PS equal to 1 over 2 V amplitude square. So this is equal to 1 over 2 times 1 over 4 V ref. So we have 1 over 8 V ref square. So the signal to noise ratio is defined as the signal power. So we have P signal normalized to P noise. And now, as we consider only the quantization noise, we take as the noise the quantization noise. Okay? I write it in more detail and say here noise. And here this is quantization noise. Okay? And we say this has to be or is equal to what? The signal power is V ref square over 8. The noise power, this is what we have calculated here. This is V ref square over 12 and 2 to the power of 2n. So I insert exactly this. Oops. Today I really mess up my drawings. So we can add this. This is the V ref square over 12 times 2 to the power of 2n. This is the signal to noise ratio. However, nobody calculates it like this. People usually take 10 times the log of this. So this is 10 times the log of the ratio of signal power to noise power. And then I have to add it here also. This is 10 times log signal power to noise power. This is what people call the signal to noise ratio. And you can, of course, simplify this expression, and then you end up with a very famous formula. This is equal to 6.02 times the number of bits n dB plus 1.76 dB. Actually, this is not the signal to noise ratio, but to be more specific, it is the signal to quantization noise ratio, because here we consider only the quantization noise. If there would be other noise sources, of course, the signal to noise ratio would be different, because then we have an additional noise term here. So we can say the signal to quantization noise ratio, the S, I put it in brackets, SQNR, is equal to 6.02 dB plus 1.76 dB. And this is a very, very important formula. Why is this? Signal to noise ratio is something you can measure easily. Often in publications people give not the number of bits, they give the signal to noise ratio. And with this equation you are able to translate the signal to noise ratio in a number of bits. I will come to that one next week again. You can use this to define an equivalent number of bits, but we will come back to this one. So far, this is a formula you should really remember, and it helps you to translate signal to noise ratio into the number of bits. The SNQR, signal to quantization noise ratio, on the left hand side, and of course, formula is important and I wrote it down wrongly. Sorry, of course the number of bits is missing here. Say something if I make mistakes, guys. Here, this is 6.02 dB times the number of bits plus 1.76 dB. So this helps you to translate here SNQR into number of bits. Okay. So what have we done so far? We started with the DAC, looked at the DAC characteristics. We saw the DAC can have an offset error and a gain error. Then we moved to the analog to digital converter. The analog to digital converter is a little bit more complicated because it contains this quantization error. We have characterized this quantization error and we have computed the signal to quantization noise ratio. So the next consequent step would be to ask, can an ADC also have an offset error or a gain error? And the answer is yes. It is defined nearly in the same way, but it looks in terms of these converter characteristics a little bit different. I made lots of pictures for you guys in order to illustrate what really happens, and you can download the slides to get an understanding of this. So we said the DAC offset error is a shift up or down in the voltage direction. For the ADC, the voltage direction is the x-axis, and the offset error is again a shift in the voltage direction. Okay, if we take this step function and shift it a little bit, then this is defining the offset error. In the ideal case, here for instance, the first step occurs right in between the 0, 0 and the 0, 1. So the ideal step would occur here at this position. Okay? However, you see that the actual step is shifted to the right. It occurs at higher voltages. So we have shifted the complete curve. And the amount in terms of voltage normalized to VLSB of this shift is defining the offset error. Here you have a little bit strange notation. You have a V0001. V, and in the index a binary number identifies the voltage position of the step. So let's say our very first step occurring here is our V01, because it's a step from 0, 0 to 0, 1. So the next step, this one, hence is called a V10, and the last step, this one, can be called V11. This is just a notation so that you understand these formulas. The offset error again is defined as the position of the first switch normalized to VLSB minus the position, the ideal position, which is 1/2 LSB. Okay? So actual position in terms of LSB minus ideal position. The gain error is a little bit more complicated. It appears as the step function is stretched in the voltage direction. So we again want a single number to quantify this stretch. So we start with the last step, which is V11. Then we take the very first step, which is V01, and we measure the voltage in between. For an ideal converter that has no gain error, this is given by 2 to the power of n minus 2. We are losing 1.5 VLSB here in the upper part and half an LSB here. This leads to this factor of 2. So this is the ideal converter. So, and if we stretch or squeeze this step function, then there is a deviation of this distance from the ideal value. And we quantize the gain error as this difference. Let me take another color, then see it better. We take this distance, which reflects in this term. We subtract the ideal distance, and the remainder is, or the rest is, the gain error. This is just a definition, but a good one in order to understand how strongly this characteristic is squeezed. By the way, if we would ask something like this in the exam, of course you have your lecture notes in the exam, so you don't have to keep this formula in mind. However, you have to understand it, and you need to know where you can find it quickly. Okay? So please understand what these step positions mean and how this formula works. That for the case that we give you a characteristics like this, you can quickly compute this. Okay. The offset and the gain error of the DAC and the ADC is the basic errors that may occur in data converters. Next week we will focus more on the nonlinear errors. And what is nonlinear errors? Well, we have seen that these DAC or ADC curves can always described somehow by a straight line. If we connect all the points in a DAC characteristics, or if we connect all these points, these points in the ADC characteristics, if we connect all these points, we end up in a straight line. Okay, and this straight line can be shifted. This is an offset error. It can be scaled. This is the gain error, but it remains a straight line. So there may be errors that apply to each individual point or to each individual step in the case of an ADC characteristics, that the step size varies independently for each step. And this is what we call a nonlinear error, because these type of errors makes this straight line to become something different. It's not a line anymore. And hence, we cannot consider the data converter as a linear building block anymore that scales our input signal. But it scales it, but it also applies some nonlinear distortion. So there is lots of definitions of nonlinearity that you can find in your lecture notes, and we will go through these definitions next week. However, I want to give you a motivation today why this nonlinearity is an issue. Let's assume we have a nonlinear system. For instance, an ADC, for instance, a DAC, can be something else. It is a system that is nonlinearly described, for instance, by an equation like this. We have an output signal that is given by the input signal. However, then we have a square term here, and this is just an example, but we may have also a third order term here. So if we would consider only this one, then we have this straight line here. This could be an ideal data converter. Input signal into the system, then a straight line shaping this input signal, and then we have the output. Very often we have these nonlinear terms, and a good, very often occurring example is that we have a compressive characteristics, that for high amplitudes we saturate somehow, like this. This can occur very often. And let's assume that we now put a sign to such a signal, to such a system. In the ideal case, we would get also this sign at the output, the same sign. However, you can see here that if the voltage increases, then we don't reach the desired value anymore, but we end up in a smaller one. So large signals are a little bit damped. This is this nonlinearity of this example. And this leads to a result that we do not reach the peak of the sine, but we damp this down here and end up in a distorted curve like this. This is the effect of nonlinearity. And this reflects in several impairments that compromise the signal processing. We come to this next week. But this should give you a motivation to go through all these definitions and the discussion of nonlinearity. It really has an impact on your signal processing because it distorts your signal. We will also see there is effects that some signals are mixed together by such nonlinear effects. Okay. This is actually not circuit design here, but it is important for circuit design, because after that we will go through all the details of how to build a DAC and how to build an ADC, and it is important that you always keep these key figures and problems in mind in order to understand why we size a certain element, we do it, or why we do things like we will do it, and how we can achieve these figures. Okay, that's it for today. Thanks a lot. See you next week.